look at this problem here. We're going to draw some charge distributions, draw some electric field lines, and then find the electric field, at least the equation for electric field for these, 7 different kind of configurations of charges and such. All right, so A, 2 positive charges. So we're going to just have a plus charge here and a plus charge here. What are the field lines going to look like for this? Well, so the charge distributions are just 2-point charges. So they're just right there. They're not spread out anywhere. We're just in 2 points. Maybe I should have said 2 positive point charges. So what happens with electric field lines? They come out of positives and go into negatives. So they're going to come out of these guys, and they come out evenly distributed. We draw, I don't know how many. They're going to come out like this, right? Evenly distributed. And perpendicular to the surface, right? They're all perpendicular to the surface. So they're all going out like this. They come out of positives. But we don't know where they're going. We don't have any negatives drawn, so we don't know where they're going. But we know they can't go to each other. So I don't know, choose one to go down and one to go up, but they're going to go away from each other, right? So they're going to go out and away from each other, off to find a negative charge somewhere, something like that. If we wanted to find the E field, just pick a point, say what is E here? E, we don't need the question mark. So E is just going to be E from charge 1 plus E from charge 2, which would be, remember, from a point charge, we've got KQ, we'll call Q1, over R1 squared, R1 hat, plus KQ2 over R2 squared, R2 hat. Whatever the vector is, R1 is a vector from 1 to here, R2 is a vector from 2 to here, so forth. But kind of general equation, something like that. 2-point charge kind of field calculations with their vector directions included, add them as vectors. Okay, good. B, a solid conducting sphere. Okay, so we've got a sphere, it's conducting. We probably should have some charge here, so let's just say a negatively charged. Right, so like in lab where we use the Van de Graaff generator, somehow we got negatively charged conducting sphere. Okay, so it's negatively charged, so it has excess charges, but it's conducting. So what does that mean? It means that the charges are going to spread out evenly spaced all over the sphere. And conducting means the charges can move, and then negatively charged means there are going to be negative charges distributed around the whole surface. 3D, all evenly spaced out. They all say, get away from me. Negative or like charges don't like each other, so they're all saying, get away from me equally much. They're not inside the sphere because they can't be inside. The field inside is 0, because if there was a field inside, charges inside, there's a field inside, then the charges would move, and we're kind of doing the static case. So they're all just sitting still outside here. In terms of the electric field lines, they'll all be coming in perpendicular to the surface. I don't know how to draw 3D, coming perpendicular in, evenly spaced. All the E field would be something like this. And if we're far enough away, just in general, we can treat a solid sphere or anything when we're outside of it as a point source. And so we just say KQ total over R squared R hat. Right? So it's going to be, again, the field is going to be, say somewhere out here is going to be, whoops, this is a negative charge, so it's going to be pointing in towards the center of the sphere from all the directions. So these lines, remember, are telling us the direction of the E field vectors. At any little point, we could just draw the tangent to it, which are all straight lines, so they're just a little piece of the line going straight in. Okay, C. solid insulator sphere. So we have an insulator sphere, and let's just say with a negative charge. Solid negatively charged. All right, it's kind of boring if there's no charges, right? So solid negatively charged sphere, and so, but it's an insulator. So we'll assume that somebody put charges on it, but they just rubbed it on something or whatever. Somehow, I guess for insulators it would have to be by friction or somehow by touch, but we will say that by friction they got negative charges on there. They don't spread out all over because it's an insulator and they can't move on insulators, so wherever they got stuck on there, they just stay there, right? And so again, the field will be perpendicular to the surface, and there could be charges inside an insulator distributed around, but anyway, so the field is something like this, and yeah, it's a little hard to do any kind of exact expression, but generally if we're far away we could use the point, kind of treat it as a point charge, but something like that. We'll call that good for that one. D, positively charged wire. D. So we're going to have just a long wire, and it's going to have a bunch of positive charges just sitting on it. So it's not a current, it's not carrying current. Current is moving charges. These are just sitting there being still, all spread out, a whole bunch of positive charges. All right, so what does the electric field look like here? Well, you can kind of think of them as a whole bunch of point charges all lined up with each other, but basically you're going to have the field coming out in 3D, all directions, right, and all spread out. So this is just, each one is a little point charge, but it's all coming out. So it'd be like you can kind of think of it as a cylinder, and on a cylinder there's just all these lines coming out in every direction, and each cylinder will have the same magnitude of electric field, same distance away, right? So at any point, if you're 2 centimeters away in this whole circle, 2 centimeters away from this point, the field's going to be the same, right? And then take a whole bunch of these circles and make them into a cylinder, right? So they're all the field lines are just going straight out from the wire in all directions. Ugh, okay. And so the electric field for this kind of a condition, we won't worry about deriving this kind of thing in this class, but the equation is, and let me just make sure I get it right, lambda over 2 pi epsilon naught r. And then we'll have an r hat. This saying r hat is just saying, anyway, unit vector pointing out, and every way out from the wire in 3D, okay? But basically all the way around in this kind of direction, making circle kind of fans. Okay, what is lambda? Lambda is linear charge density. Which is coulombs per meter. So how many charges, coulombs of charge per each little piece of the wire, coulombs per meter, do we have here? So if we had a foot-long wire and we had 2 coulombs, we would have 2 coulombs. I'm sorry, let's say a meter-long wire and 2 coulombs, we would have 2 coulombs per meter would be our lambda, right? So we could calculate lambda as the total charge Q divided by the total length L, something like that. But if we want the charge for any certain length, we could say Q is lambda times, say, delta X, whatever length we have of wire. All right, so that's what lambda is, linear charge density. Epsilon naught is just another constant. We had Coulomb's constant K is 1 over 4 pi epsilon naught. Epsilon naught is 8.854 10 to the negative 12. Let's see, coulombs squared per Newton meter squared, I believe. Did I have that written in my cheat sheet? Yes, that looks right. Okay, so that's what the pieces of that equation hopefully make sense. All right, that was D. Let's look at E, a negatively charged wire with a positive charge nearby. Negative wire with a positive charge nearby. So we're going to have just a wire that has a whole bunch of negative charges. It's a conductor. Wires are conductors generally. We'll assume it's a conducting wire. So this negative charge is all around the outside of this little skinny wire. And then we're going to just have a positive charge up here. Okay. And I guess for now, let's kind of assume they're pretty much the same size. So what's going to happen? How do we have, what do the field lines look like? We're going to have the field lines, they're perpendicular coming out of here, and let's try again. All right, so around the point charge, they're going to come out all perpendicular, but then they're all going to come down to the minuses over here somehow. Kind of cheating here. All right, so we're going to be perpendicular when they hit the wire. It's going to be coming straight in at right angles. And then they're perpendicular to the surface here, which is round. It's a little hard to draw. Coming out of there. All right, and so they always leave positives and go to negatives, so the E field is something like that. E. All right, and if we want to know the E field at some point here, E total will just be E of the point plus E of the line, or E of the wire, as vectors. And so it'll be kind of a mess. We probably won't have you actually calculate stuff. So we use our equation here for this equation for E of the wire, and we use our point charge equation for E, and then we would have to add them up at that point. Again, I probably won't do anything that complicated for this class. F. But you can at least draw the shape, draw the lines is what I'm looking for here. F, a hollow conducting sphere with a positive charge inside. So we're going to try to draw 3D here. So we've got a conducting sphere. Okay, 3D and look inside. That's not going to be working very well. All right, so this is a sphere, but then it's like a hollow shell. It's like an egg shell, but it's maybe got some depth to it. All right, so this is a hollow sphere. Hollow sphere. And we have a point charge inside. Okay? So it's like the little tiny baby yolk inside of an egg, but it's a round, perfectly round egg. Okay. And so we have some, what did I say, if it's positive or negatively charged, nope. Hollow conducting sphere with positive charge inside. So we got positive charge in here, some sort of positive charge on something. All right. And so this is a conducting sphere. I think I said it's a conducting sphere. Conducting sphere, yes. And so it doesn't say it has any charge. So we'll assume that it was not charged, no net charge at the beginning, right? And somehow we got this little charge inside without getting any charge on the ball. Maybe think of a tennis ball with some little dot in the side, some little dot of charges inside it. Somehow it got in there. All right, but then this is closed up. So now what happens? But this is a conducting tennis ball, so it's a metal tennis ball. All right, anyway. So what's going to happen here? So the conductor has electrons that are able to move, right? And so if I started off as neutral, it still is neutral because it says not grounded, it's not charged. And so it has the same number of positive and negative charges, but since this is inside, some of the electrons are going to be free to move, and they're going to come around and line the inside of this, trying to get to those positive charges, right? Because opposites attract, and these electrons inside the conductor can move, so they're going to come here. And so if we have a positive Q amount of charge inside, we're going to get a negative Q amount of charge from the inside of the conductor is going to try to get to those positive charges, so it's going to line up and make like a little film of negative charges on the inside of the conductor. Well, then what happens? Well, when that happens, then they leave behind pluses, excess plus charges that were matched up with a minus, but now they got left behind because they wanted to go in, these electrons wanted to get close to those, so now we have an excess positive charge now on the outside. And so remembering that positive charges don't really move in conductors, it's the negative charges that move, but the negative charges are going to move such that the distribution looks like this. All right, so the excess charges are not inside. Excess charges are on the surfaces, but it has an inside surface and an outside surface. All right, inside a conductor, E is always 0. So inside the shell, there's no field. From here to here, the field is going to go from positive to negative, so the E field inside the hollowness of the thing is going to be going from the center out, and same thing here. The E field on the outside, since we have positive charges on the outside, is going to be going 3D. I can't draw 3D very well, but 3D out from here. And so if you were trying to get the E field out here, we could just consider it as a point charge, right? And the net charge inside of here, or just basically we're just going to see the outside, the net charge is going to be Q, so it's going to be KQ over R squared, R hat again, all straight out. Okay, so some things to remember. Inside conductors, the E field is always 0. Inside the actual material of the conductors, you can't have any electric field when we're in the static conditions like this. I guess this should be a vector. And then, but the charges inside a conductor can move, so they will try to go towards and separate themselves out. So once a motion is done, then this is what the picture would look like. All right, because they would be attracted, and then we would have some left over, that positives that couldn't move, but they end up being the ones without the electrons end up being, after all the motion gets finalized, on the outside. Okay, so what else? If this were let's see what the next one is. Oppositely charged parallel plates. Okay, so if this were an insulator, what would happen? If this were an insulator, we put charged particles in there, this whole thing, nothing would happen, right? Because it's insulating, and so there wouldn't be these negatives coming to the inside. The positives would go to the outside. They'd all just stay where they were because they can't move in insulators. But the outside electric field would still be the same, right? Because we would have that point charge inside there. All right. And inside here, we could do the same kind of equation for the point charge inside the field, right? Or inside the shell. All right. So last one, G. 2 parallel plates. So we got 2, we'll just say they're like these flat plates. Probably normally would be closer together. We were making what we call a capacitor. We'll get to that later. But we've got 2 rectangular conducting plates, oppositely charged parallel plates. We'll assume they're conductors. All right, and so we'll say that the conductors, so they will have, just try to draw it evenly spaced, and this should be on the bottom, because if one is negatively charged, the other is positively charged. They will be the free charges will align such that the positive ones are facing the negatives ones. So these negatives should be, see, there's a super, super thin, or the negatives being underneath, actually, although I drew them like they're on top. All right, and so what's going to happen? The charges come to the surfaces and try to go towards each other, so they're attracted into the inside of this little sandwich. All right, and so then I didn't draw that very well. Maybe I shouldn't have drawn them showing there. Anyway, this is like a see-through plate, and they're on the bottom. And then what does the electric field look like? Electric field goes from positive to negative, so the electric field will just be going straight up in this case, since all the positives are down, and just straight up everywhere. inside, right? On the outside edges, that might bulge a little bit out, but it starts here, ends there, and we would also often call this a uniform electric field, and at least in the center, not close to the edges, we can just assume a straight, very nice straight line electric field. So sometimes when we talk about putting an electron or something in a uniform field, we probably lots of times might generate it by having parallel plates, right? And so the formula for E inside of a between two parallel plates is sigma over epsilon naught. All right, and notice it doesn't depend on where we are. If we call this the y, if we have like an x and y direction here, it doesn't depend on y at all, or x. And so close to this plate, close to that plate, in between the plates, wherever we are, it's the same, right? Sigma is the surface charge density. Surface charge density. So just like we had linear charge density before, it was coulombs per meter, this is coulombs per square meter. All right, so it's how much charge is spread out per area, per square meter. And so in general, then we could say sigma is the total charge divided by the total area. Or if we want to get charge for any little piece of this little piece here, how much Q is in that little area, is going to be sigma times that little area, AX or whatever we want to call it. Okay, so surface charge density, coulombs per square meter, and then epsilon naught, of course, is the constant that we had before, 8.854 10 to the negative 12. Okay, I think that's all of them. All right, so there we go.